so far we have discussed the fundamental concepts of statistical mechanics. So what we'll do today is we'll start on some applications. But before we can go and do some applications, I want to do some background. So let me say a few things first about applications. So our applications will mainly be quite simple systems, some classical systems, and which will involve mainly gases, and also a few quantum mechanical systems. Okay. Now I understand that most of you haven't had quantum mechanics. Even the classical mechanics that you've had have been mostly Newton's law, right? Like mostly Newton's law, and a little bit of, ENM. But even the ENM that you've had are not the advanced Maxwell's equations, not in the differential form at least. So what I'll do is that, just to bring everyone onto the same page, and this is something I enjoy doing quite a lot, is to give you a little bit of a background, both of the background on how to think about classical mechanics and quantum mechanics, okay? So at the natural junctures, I will tell you a little bit about the background. So before we jump into classical systems, mainly gases, I wanted to give you a brief, like a one lecture introduction to Lagrangian and the Hamiltonian formulation of classical mechanics. Okay, is that all right?
Yes, sir.
Okay. I mean, some of you have had this, right? But a lot of you haven't, I think. How many of you had seen this?
I have physics 204. I took.
Okay.
I have, sir.
Okay. And?
I mean, classical mechanics course.
Okay, 3, 4.
Yes, sir. Saw this back in CM, but
5,
kind of rusty.
Classical mechanics, sir.
6.
Even
if even if most of you have seen it, I think it's a good idea to just review it. What do you think?
Sir.
I mean, it's been a while since we last one.
Yeah, so I think it's a good idea to review it. Okay. Okay, let me just I saw that Sitima is here. So anyone who missed the first round of
Dipro.
Dipro?
Muhammad Abdullah.
All right. Okay. Anyone else? Okay. So let's get on. So this today's lecture is actually not going to be StatMech, but about Lagrangians and Hamiltonians. And I think that even if you've seen this, it's always good to see it again, because at least for a few times, then some of the stuff that you thought you knew, is kind of, you realize, oh, there's some new things, some important things that you missed, stuff like that. Okay, so please ask questions, because it'll be new for some of you. So first, let's start with Lagrangians. So let's take the simplest system that we can think about, which is, a particle well, it's actually not the simplest, next to the simplest, a particle in one dimension, experiencing a force. So we know that that's given by Newton's law, which is F equals to ma, right? Now, in one dimension, a vector is a function because it can be positive or negative. So I'm not gonna, if for a higher dimension, this should be a vector equation, but in one dimension, it doesn't matter, right? So how does this equation look like if I introduce the notion of a potential? So tell me, someone, how is a potential related to force? Can someone tell me?
F equals minus dv dx.
Right. So this is going to be F equals to minus dv by dx. And I'm just using partial derivatives because I'm assuming potential is probably not a depend, it doesn't depend on time, but in higher dimension, this partial would actually make sense, but in 1D it doesn't matter. So in higher dimension, the force would be a vector, and the potential would be the minus of the gradient of the potential, right? So this equation then looks like minus dv by dx is equal to mx double dot. Okay, so this is the most basic and the fundamental equation in classical mechanics, unless we think about Maxwell's equation, which we are not going to do right now. So now let's consider this particle, the trajectory of this particle, right? So the trajectory of the particle we can plot on a two-dimensional graph, and let's take the x-axis to be the t-axis and the y-axis to be the position of the particle, which is x. And suppose the particle starts with at some time t0 and ends up at, the final time is tf, and the position of the particle initially is, say, x0, and the final position is something like x of f. And so this is, and the trajectory of the particle can be something complicated like this, right? And it'll depend on the, what will the shape of the trajectory depend on? It'll depend on the initial conditions, the position and the velocity of the particle at this point in time, and the potential v, right? The potential v is going to influence this particle. So in general, we shall denote the path of the particle or the trajectory of the particle as a function of t, x of t. So this is the path of the particle. Okay, so now what we're going to do is that we're going to reformulate Newton's law in terms as an integral principle, not a differential principle, that is subject to the boundary conditions x0 at x at time 0 and x of f at time t of f, okay? So this principle is called principle of least action. Okay, so before we can define the principle, we can state the principle, we need a few definitions. The first definition is, let's define something called L, which is the kinetic energy minus the potential energy of the particle. Okay? And this thing has a name, it's called the Lagrangian, named after Lagrange. The whole Lagrange point thing that you learned in Newtonian physics at some point. Okay? So the Lagrangian is not the kinetic energy plus the potential energy, it's the minus, okay? And you might say, yeah, that doesn't make sense. I mean, the sum of the two energies is what the total energy is, and that is going to be conserved. And you would be right. But the Lagrangian is not something that is conserved. It has something which has a different purpose, okay? And we shall see that shortly. It turns out that the Lagrangian plays a very important role in quantum physics. So the Lagrangian is a function in general of the position of the particle and its velocity, okay? Why is that? Because if I look at the kinetic energy of the particle will be something like 1/2 mx dot squared, right? Which is this dependence. And if I look at the potential energy can be many different things, but if you're looking at, say, a conservative system, then the potential energy would be just a function of the position, right? So in general, we take the Lagrangian to be a function of both the position and the velocity. Note that the Lagrangian usually doesn't depend on higher derivatives of x, okay? My electricity has come back, yay. Anyway, so I am going to attempt to switch to the Wi-Fi. If I get cut off for a minute, I will be back, okay? You guys can hear me, right?
Yes, sir.
Yes, sir.
Yes, sir.
Let me wait a minute because I think it'll take a few minutes for the router to actually, come back online. Okay. Anyway, let's carry on. Any questions so far?
Sir, when you say higher derivatives, you mean dv, dx, and higher, right?
No, I mean time derivative, like x double dot or x triple dot. Time derivative, okay?
Oh, I see. Okay.
X dot is dx by dt, okay? So I mean that the Lagrangian, so, the equation of motion, Newton's law has x double dot, the acceleration, right? But the energy and the momentum and the kinetic and the potential energy, they don't, right? I mean, if I take a particle's, momentum and I integrate that, I basically get the kinetic energy, right? The F term, the ma term in Newton's law, when I integrated, over time, that is, over space, that is basically what gives me the hang on, what do I mean? X double dot. Yeah, so the energy is the first integral, the total energy is the first integral of the equation of motion, right? And that that depends only on x dot. It does not depend on x double dot. Okay, so that's why usually in physics our equations of motions are second order in time at most, and therefore the Lagrangian is going to be first order in time. Okay.
So that after integrating, it becomes second order?
No, I mean after this, we'll see how the Lagrangian yields the equation of motion. We have not done that yet. Yeah, you'll see soon. Okay. So all I'm saying is that, let's just, if I define the Lagrangian in this way, which is the difference of the kinetic energy and the potential energy, then of course this makes total sense, right? Because usually potential energies don't depend on, on anything other than the position. I mean, if, for example, you have a system which dissipates energy, so say it loses energy through friction, then of course the potential energy usually has a velocity dependent term. But if it's a conservative system, you never have a velocity dependent term, right? So let's look at some common potential energy functions, right? So for example, for the case of gravity, it's just like 1 over r. So this is same for gravity as well as for electromagnetism, right? Or electrostatics, right? And if you're looking at the potential energy of a particle in a one-dimensional, near the Earth, then its potential energy is just proportional to the height, right? Which is just, it's proportional to x. Okay, so let's carry on. So once we have defined the Lagrangian, we can define something called the action. Okay? And the action is the Lagrangian integrated over time from the initial time t0 to the final time t of f. Okay, so this is the action. Okay, so because, the particle takes some trajectory, right? The particle has a trajectory. So let's look at a trajectory here. So the function x, this is the trajectory x. It depends on t. And therefore, if you knew what this function was, you could figure out what x dot of t was as well, right? So if you knew those two functions, you could plug them into your expression for the Lagrangian, and then you could just do the integration with respect to t. So this is the action. Then what is the principle of least action? The principle of least action says so the principle of least action states that the path that the particle takes that is the physical path from x at t naught to x at tf is the one that extremizes or minimizes. I said least action, but it's actually extreme action, or extremizes or minimizes the action. Okay. So this is the principle of least action. So what does this mean? So this is a little bit of a, it's not obvious what this means. So the idea is something like this. You have t here and you have x here, and this is your initial point, and this is your final point. And there are many paths which can connect these two initial and final points, right? There are an infinite number of paths. Do you agree?
Yes, sir.
Can you hear me? Okay, good. So there are an infinite number of paths. Which path does the particle actually take? Obviously, it's the path that satisfies Newton's law, right? But we are not going to use Newton's law. We don't want to use Newton's law here. We want to come up with a new way of formulating mechanics. So what the principle of least action says is that the path that the particle takes is the one which extremizes the action, meaning that if I now say take one of these paths, suppose I take, and then I just change the path slightly, like infinitesimally, say, then that's going to change the action, right? Because this integral will be a different integral, right? Because the Lagrangian, this path there would be different. This integral will give you a different value. So this action S will change, right? But it'll change. Whether it'll change rapidly or not, we don't know. And what the principle of least action is saying is that for the physical path, suppose the physical path is the one which is, say this one. If I look at the paths which are infinitesimally different from this path, then the action will not change, because that path is the minimum. Okay, so it's like this. If you have some function, say some function of, say, x, we want to find its minimum, what do? Minimum or maximum, we say, okay, we have to solve this equation, right? But here what we are doing is that we are saying that we are going to change our physical paths infinitesimally, and for the path for which this change leads to S not changing. So for most of the paths, S will change by some amount, where this is not zero. This is not zero. But for the physical path, this thing will be zero, okay? That's what this is saying. These are subtle points, subtle questions, okay?
Sir, so like the particle will be taking the path with the minimal action, right?
Yeah, exactly.
So when I first studied about it, like it was said that the particle would smell all the paths and take the path of the least action.
Yeah.
But then when I read Shankar for quantum mechanics, he said something completely different. Instead of saying that the particle smells all the paths and takes the path of the least action, the particle follows the Euler-Lagrange equation at every instant. So my question is, does this question even have a objective answer, or is it completely subjective?
Well, it's, I mean, the particle smelling all the paths is kind of a, it's a picturesque way of saying things. In classical mechanics, that's not true. In classical mechanics, the particle at every point in time has a well-defined position and momentum, right?
Mm-hmm.
So the particle is, it's better to think about it as it, like following the Euler-Lagrange equation. But since I have not derived the Euler-Lagrange equation yet, can we just postpone the discussion of this question until we do? Okay, good. Any other questions so far about the material we've covered? Okay. If not, let me just like go and prove this statement.